Okay, welcome. So today we're going to talk about DC motors. So let's go to the PowerPoint slides and look. The first thing is that we're talking about electric motors. We can see that electric motors can work both directions. So we have a motor based where we apply electrical power and we get mechanical power out. And so that's where we're basically flowing this direction, and that's called a motor. And if we're in generator mode, we're going the other direction. So we have a mechanical system that causes the motor to rotate and it produces electrical power out. So lots of times they call them electrical machines rather than electrical motors. So a motor is going this direction, a generator is going that direction, and then machine is just the general term for it. Okay, so let's look at the basic structure of a motor. So here is an opened motor, and you can see that there's one part that's kind of locked down, and that's called the stator. And then you have the part in the middle that rotates, and that's called the rotor. So again, if we take a cross-sectional cut, here is the stator around the outside, here is the rotor on the inside that rotates around. Here's a motor with the two pieces taken apart, so this is the stator with an electromagnet on the outside, and here is the rotor with some windings on the inside. So electric machines, there's all sorts of sizes. We have generators that are up in these big size like steam turbines, and we have general purpose motors. You can see here's a set of motors. These are probably like pumps or something like that. And then you got these really small motors. So you can see everything from generators, hydroelectric plants, wind turbines, the alternator in your car. We have motors like fans and blowers and pumps and compressors and cranes and drills and saws and all sorts of stuff. Anything that we want to do something are using some type of electric motor typically. So let's look at the basic principles. So the basic principles are if we run a current through a wire loop, that's going to produce a force if it's in a DC magnetic field, and then it's also going to produce an induced voltage across there. But this is going to cause this to rotate around. So here is the basic structure of a simple brushed DC motor. This one's using permanent magnets, and then you have a current that flows through this wire loop, and you have these commutators and brushes that change the direction. So let's look at this video right here on YouTube.
Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. Unlike the other electrical machines, DC motors exhibit a unique characteristic: the production of back EMF. A rotating loop in magnetic field will produce an EMF according to the principle of electromagnetic induction. The case of rotating armature loops is also the same. An internal EMF will be induced that opposes the applied input voltage. The back EMF reduces armature current by a large amount.
Okay, so now let's look at the basic parts and go into more detail on our electric motor. So there's two basic types. We have the permanent magnet, where you basically have a permanent magnet in the stator. This is usually used for small motors. Anything larger, you create a wire wrapping around parts of the stator to create an electromagnet. So let's go over some of these basic principles. So we have Faraday's law and Lenz's force law. So in Faraday's law, the induced voltage on a wire loop is equal to the number of turns times the change in flux. So you can see as this wire loops around, you're going to have a different amount of flux that goes through the wire loop. If it's perpendicular, it's a maximum. If it's in line this direction, it's going to be a minimum. And then the Lenz's force law is the force on a wire is equal to IL cross B. So you can see right here the current's going up. My magnetic field's going this direction, so that's going to cause a force this direction. Over here, the current's going down. Magnetic field is this direction. That's going to cause a force that direction. Since there are two forces on this, we do that in terms of a torque. So a torque is basically equal to the force times the radius away from the rotation axis. So these are the basic principles. So then we're going to go into detail, and so what we see here is the induced voltage is going to be equal to N times my fixed magnetic field times the change in the area, and this area is changing as it loops around. So when we take the derivative of this, we get this equation here. So we get the number of turns times the magnetic flux density, the size of the loop, times the derivative, and so the derivative is going to pull out the omega havoc because it's a sinusoidally rotating structure. Then our force is equal to IL cross B. So here is our B. We have N loops, and so N times L crossed with the I gives this, and so this is going to be our maximum force if everything is perpendicular. So when we're done, we get these two equations. We get an induced voltage on the line, which is a function of this term and the speed, and we get a torque, which is equal to the current through the loop. So if we reorganize these, you see that they both have these coefficients. So the voltage is equal to some coefficient times the speed. The torque is equal to some coefficient times the current. And you see that these two terms are exactly the same. So the induced voltage coefficient and the induced torque coefficient are equal as long as you're using SI units, which means volts, amps, Newton meters, and radians per second. So here is our equivalent circuit. So we have some resistance in the lines, we have some inductance because it's basically a big wire loop, and then we have an induced voltage on it, and this is called back EMF. And this is a function of how fast your motor is rotating. And we can also get the torque produced by the motor, which is equal to K times I. So again, here we see that higher current produces higher torque. High speed reduces the current from the back EMF. So eventually we get so much back EMF that the motor starts to slow down. And we have two types of power. We have electrical power, which is our voltage times the current. So that's going to be the voltage across these times the current going through here. And we have mechanical power, which is the torque times the speed out here. So we have electrical power and mechanical power. So solving this circuit, we see that our current is basically going to be equal to the terminal voltage minus the back EMF divided by the resistance. The current times my coefficient gives me my torque. So then this becomes my torque equation. So you see from this equation that we get maximum torque when my speed is 0. So at speed 0, I get maximum torque. That's up here. And if I have 0 torque, meaning 0 current, that's going to be the case when my voltage equals my back EMF. So this, solving this part right here, is going to get me my maximum speed. So my maximum speed is V over K. And you see from this equation right here that we get a linear change between our torque and speed. So this is called your torque speed plot. And that's the basics of motors. So let's go look at a motor spec really quick. Okay, so here's a spec for a set of motors by Electrocraft. I just found something online. So here is a motor. So if we look at these specs, they got these different motors. Each column is a different motor, okay? And so with this one, they give you that this has a maximum terminal voltage of 60 volts. We come in here, and here are my coefficients. Here's my torque coefficient. Here's my back EMF coefficient. Here is my terminal resistance. And if I look at these, so these are basically torque versus speed plots. And before we showed that they were linear, but you see that these aren't perfectly linear because you have a maximum current. So if you exceed this current, this maximum peak current or this maximum peak current, then you're going to melt the wires and the motor's going to break. So this would keep going up, but we have a maximum torque, which means I have a maximum current, otherwise you burn out the motor. And then we have this continuous operating one, so if we operate above this point, then it's going to heat up again. So again, this is very intermittent, so instead of going all the way up, it kind of flattens off and goes down like this. And then this is your continuous one, is even less in terms of heating up. And so that is the quick overview of DC motors.